Right, so in this one here, why does computer store information as a series of zeros and ones for 2 marks? Essentially, the thing to remember is that computers don't choose to store numbers as zeros or ones. It's just how they're made. And imagine they're made up, which they are, of these tiny little um, things called transistors. And what these are electronic switches. They're switches, but they're not like a little bit of metal that moves across because that would be quite slow. They're switches that act on a level of physics, so they change a property of it. You may have heard of something called a semiconductor, and that's what silicon, which is sort of sand, which is basically what CPUs are made out of. And the reason it's called a semiconductor is because it can or cannot, it can be altered to either conduct, one, or not conduct, electricity, which would be a zero. And I'm not going to get into the way it does that because that's quite complicated. But in simplest terms, computers are built up of electronic switches. And because they're electronic switches, they only have two states. So if you imagine here, I've faked 4 switches, A, B, C, and D. And I've got them in the state of on, off, on. How can that represent anything? Well, what someone thought was, why don't we allocate a value to each column? Okay, so this switch is worth 1, this is worth 2, 4, and 8. So if we go down here, and instead of off and on, we do 1 and 0. So we've got a 1 in the 1 column, nothing in the 2 column, nothing in the 4 column, and 1 in the 8 column. So this, in fact, would be 8 plus 1 equals 9. So this would be how you would represent 9 in binary. And so the reason the computer does this has nothing to do with simplicity or speed. It's simply because they're built up of switches, and switches can only be in one of two states, which we then allocate a 0 or a 1 to. Right, this one here. This is the trickiest one in the whole course, probably. On the whole, probably the whole course. Give the 5 steps of the fetch, decode, execute cycle. So the fetch, decode, execute cycle is basically what the computer is going through over and over and over again on a loop until the program stops. And then it does nothing. It waits for the next fetch, decode, execute cycle to begin. So a program is running. Now the program is in memory somewhere, in RAM. Okay? So somewhere there's memory addresses that are numbered. They're in binary, but for simplicity here, I haven't put them in binary. So you can imagine somewhere in RAM, there's an address, and then some data like this. So there'll be 4610, might have been, I don't know, add 12. Okay, 4611, subtract 3. Okay, so this is the program. And we're at 4612. So 4612, we'll do that as add 9, whatever. And then there'll be 4613 and so on and so forth. I'll do halt, which is end program. Okay, there we go. So you can imagine this is in RAM. Okay, somewhere in these chips. Doesn't matter where. But we know it's at these addresses. Now, currently, we're about to execute this instruction here. And we know that because the program counter points to the next instruction. It's the address of the next instruction to be executed. So it's like, where is the next instruction? So we need to fetch. So in the first part of the fetch, code, execute cycle, which is the only difficult bit you've got to know, is the fetch part. Okay? So how do we get that out of RAM? Right? And this is how we do it. We copy the program counter into the memory address register. Okay? Then, it doesn't matter to you. You don't have to know about this in the GCSE, but just understand it goes down these wires to RAM under what's called a memory controller. And then that little memory controller will look and say, hold on a minute. What's in 4612? 612's got add 9. Okay. And then that will go back from RAM into the MDR. So step 1 is program counter is copied into there. Then data is fetched from that address and it turns up in here. Okay. Now, whilst that's happening, just as that happens, this goes up by 1. So that we go on to the next instruction, obviously. Ready for next one. And then this instruction is simply decoded because it's got to look at it, split it in half. It's got add, it's got the number, so there's 2 parts to it. It's got to see what bit of the processor is going to do it because there's different bits for different, instructions. So it's got to decode it. Oh, what I've got to do with it? And then it's going to execute it and repeat. So that's basically what happens in the fetch, decode, execute cycle. And then this would happen again, obviously. So then program counter would get copied into here. This would go over to RAM. The memory controller would send back the instruction found there. And put it in there to be decoded and executed. And of course, this would be incremented and the cycle would repeat. But of course, in this case, halt means stop program. So it would stop. But that was just a specific one. Okay, so that is the main steps of the fetch, decode, execute cycle. Okay, so on to the next question. In the von Neumann architecture, what 2 things are stored in RAM? Well, basically, in your RAM chip here, let's get this RAM chip from here, so I drew it, might as well use it. There are 2 things, okay? When you execute a program, you run the program on your phone or on your computer. I'm going to do paint.exe. I've already loaded it for this purpose. But basically, the first step loading does is put the program into RAM. It might not put all the program into RAM because the program might be too big and it might not be efficient enough to do that. But it will basically stick the program, there you go, there's paint, all nice and small, in RAM. It's loaded the program into there. Okay? There's paint.exe. Let's say it took this entire chip's worth of memory to do it, which I very much doubt it would. So the first thing it loads up is the program instructions. The instructions are these, the executable. So here is paint.exe loaded. Okay, so that's in RAM at the moment. Somewhere in my memory, I could... that word is somewhere there. These words are somewhere in RAM. If I could find them and edit them, these would all change. This, all in RAM. Now... Now the other bit that's in RAM is basically the data associated with the program. So with the paint program, it's obviously the image. So this image, this red circle, is somewhere in RAM. Somewhere. And if I could edit the data, the binary data, these pixels would change. I could find it somehow by doing some sort of memory scan. And then eventually I could just start putting random numbers to it and hope I don't crash it. But it would just like dots would appear on in the image. Okay. Because it is just stored in RAM as binary data. These colors will be given a number. All right. And like that could be 0, 1, 2, 3, whatever. And then I'll put the number 4 somewhere. And now that all of that, is colored. Okay. So the program itself, the program instructions, and any program data is also in RAM. And that is what's in the von Neumann architecture. You might think to yourself, and ignore this if you don't want to know any extra information or you're not interested personally in finding out more, what are the alternatives to this? Well, the alternative is that you have separate RAM. You have RAM that you have for the program instructions, and you have different RAM for the data, which is in something called the Harvard architecture, which is in fact better in some ways because it's faster, but it isn't as flexible. But anyway, so that's the other alternative. But in the von Neumann, we store the data and the instructions in the same place, in the same memory. Okay. Okay, so on to question 4. Looking at the 2 computers here, Sarah says that CPU 1 is always going to be better than CPU 2, as 4 times 2.3 equals 9.2 gigahertz, 9.2 billion, which beats 4.6 times 2 equals 7.2 gigahertz. So basically they're saying the quad core is always going to be faster because it can simply perform 9.2 as opposed to 7.2. Now essentially this would normally be the case. It's very likely that the quad core would be a faster computer. But 2 things. First of all, as some of you mentioned correctly, there is a higher cache size here. Ignore the fitment irrelevance. I don't know why they put that in the exam, but it's normally called socket. A fitment's weird. But anyway, cache size does matter, and so having more cache makes it more likely, but that's another question which we'll go through later. So that is one thing. Yeah, the cache is higher, so that's better for a computer too. But it's also got a significantly higher clock speed. So imagine I was performing a single task, one job that I can't spread around to other things, then it would be much better to use the dual core processor. I might not even be able to use a second core, so I might be only able to use one core. The 3.6 billion beats 2.3 billion. But so basically, the quad core would only be more useful if we're either running a large number of programs, that obviously each program can then be put on a different core, or if we're running a program that has the ability to make use of multiple cores, which is not all programs. Okay, if I have some AI, that works very well on lots of cores, because AI tends to try out lots of different ideas and pick the best. So I can stick the different ideas on different cores. They can try out their ideas, and at the end I pick which one got the highest score, which is basically a lot of how AI works. But that's only possible if I can split the task up. Okay, and not all tasks on a computer can be split up because they simply need other tasks to finish before they can continue. I always use the example, but it is one of the best. A very standard computer game is like that. I need the enemy to move and then shoot and then do things in a very sequential manner. If I have the game running sort of on different cores, it's going to be, I won't be able to move on until certain things are done, and that can be quite tricky. Some parts of a game can be put onto different cores, sound, because sound can be a millionth of a second out. Who cares? Because computers are fast. We are talking millionths of a second, but that you can't be even a little bit out in the logic of a game, because health has to go down, things have to happen the same every time. So some software works really well with multiple cores, web browsers, any image editing, video editing does, AI, data analysis, they work really well with lots of cores, and some don't. So the answer simply for this is not running enough programs, or the programs can't make use of multiple cores, and of course the cache was bigger as well, which a lot of you noticed. Well, I'll do these two questions at the same time because they kind of similar. What is a register? A register is just a really, let's go back here. It's just a really small, ultra fast bit of storage. That's all it is. Think of it as a box. It's a piece of memory, a bit like RAM, but it's way quicker. It's small, ultra fast, normally inside the CPU, like these are inside the CPU. Okay. Now, they can hold normally one of two things, and this is what I think confuses. They either hold an address or data like this, you see? So earlier on, for example, remember if you watched the other one, but if you didn't, it's fine. In the fetch code execute cycle, obviously the program counter gets copied here. That goes across, and then back comes the data, which was add 9. Boom. So the memory address register holds an address. An address is a place in main memory, a place in RAM. That's what it means. So it either holds an address or the data. You can think of it as it either holds, like think of it as a letter. I know the letter's one thing, but imagine that an address is the front of the letter and the data is what's inside the letter or the package or whatever. So you get data registers and address registers. So here, the program counter and the MAR are two address registers. They only hold addresses. They hold the address. The program counter holds the address of the next instruction to execute. And the memory address register holds the address of where we want to get stuff or put stuff from RAM. So it's where we're going to, where we're fetching from. Right? Now, some of you accidentally, which is fair enough, because I think I might have done this if I didn't look carefully, did an address register, but it did say two data registers. So there's one data register here because that holds the data, the MDR. The other data register was the accumulator because that holds like the answer to maths. And obviously maths is numbers that aren't addresses. They're not like address 4613, right? There might be the number 4613, but it would mean the number 4613. So the accumulator and the MDR are both data registers. They store data, numbers, or instructions, colors of pixels. They can store a letter, a part of a string, pi, whatever. Addresses, they would store the addresses of RAM of where data is stored. So if, for example, we were to save pi into RAM 4614 and put 3.141, oh god, 159, is it? I don't know. 2, something like that. I know one of you out there is going to know pi to like 100 digits. So if I were to load that from memory, okay, fetch it, it would end up in the MDR, because the MDR would have the pi bit and the MAR would have the address I want to load it from. Okay, so let's say the execute was to load from memory. Okay, I would load that and it would load it into there. It would probably copy it into the accumulator, but that depends on what the instruction does. So there are two types of registers: address, data. There you go. Right, now explain what cache is and why having more cache might make a computer run faster. So it's two parts to this. What is cache and why having more of it's better? So what is cache? Well, during the fetch to code execute cycle, the slowest part is RAM. Okay, the slowest part is getting stuff from here into here. So I'll delete that because I copied it from the other thing. Okay, so let's say we're at this situation. Before, if you watched the video, but if you didn't, then you should know that gets copied into there, that gets sent across there. I'm just repeating myself every 10 seconds now. This goes here, and then add 9 would come back here. Boom. Now, the thing is, computers loop a lot. They're stuck in loops doing the same thing. Think about a game. It's going round and round in circles going, have you pressed the key? Have you pressed the key? Have you pressed the key? Have you pressed shoot? Have you moved the mouse? Have you moved the mouse? Have you moved the mouse? So it's asking the same instructions. It's executing the same instructions over and over again. So what happened is, what cache does, it stores the frequently used instructions. So let's say here, these 3 instructions keep getting used over and over and over and over again. Okay? Well, let's say that here, cache can only store 3 instructions, actually. Boom. It's only got the ability to store 3 instructions. Just to be clear, cache is a lot bigger than this. I'm not going to get into the sizes of it. You get different levels of cache. It can be more complicated, but don't worry too much. But in this fake example, cache can only store 3 instructions and data. Okay? So what it does, before it fetches it from RAM, it will look to see if it's in here. If it's in here, it will quickly chuck it in there. And this is nearly instant, just to be clear. This is nearly instant. And cache is so quick, it happens like nearly instantly. So now we've essentially skipped the fetch because we've got it from cache as opposed to have to go into the much slower RAM. So that's why it makes it faster. Because if the data we want is in cache rather than in RAM, we can, well, not rather than, as well as in RAM, but if it's in cache, we can immediately get it from there and put it into the MDR. Now you might say, how is cache so much faster than RAM? Well, they make it faster, and the fact that it's actually in the CPU makes a difference. Now you might think, why don't they make the stuff they make cache out of? RAM, basically cost. It's quite expensive. Cache is a lot smaller than like the RAM that we need nowadays. They can do it, of course, and I'm sure they do in some sort. I'm sure Google have computers with ridiculously fast RAM, blah, 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 especially bespoke systems or some crazy stuff NASA's got. But for general purpose computers that we use, it would just be so expensive to make RAM out of the stuff that cache uses. And I think it would use quite a lot of power as well. Coupled with the fact that it's also, it's the fact that it's inside the CPU that makes a difference. I know you might not think that the length of the wire and going across that motherboard makes a difference, but it actually does. When you're talking about billions of times a second, it does anyway. Right, so that's what cache is. It's very fast storage inside the CPU that stores frequently used data or instructions. So the computer can check before it fetches from RAM if the data is in cache and get it from there, which is much faster. Now, why would having more cache better? Well, more cache just means it's more likely that it's in cache, okay? If I had only one slot here, which obviously is weird, right? Now my 4612 is not in cache, right? And I can only store one thing in there. If I have 3 times the amount of cache, then theoretically it's 3 times as likely what I need is in cache. Therefore, I'm getting more cache hits, you know, where the stuff I want's in cache, and therefore that should speed up the process. That's basically cache. Well, I'll just chuck these two together because number 8 is so easy and quick, and there's not much to say about it. The component inside the CPU that performs logic checks, which is basically checking like, is this number bigger than this number? Is this number, you know, times whatever bigger than this number? And the maths is the arithmetic logic unit. A lot of people get it mixed up with the accumulator. The accumulator is where the arithmetic logic unit stores the answer. So if I did 7 plus 12, it will store the answer in here. Okay, but it's the arithmetic logic unit that's doing it. Registers, which are these 4 things, don't do anything. They're boxes, they're memory. They just have things put in them or taken out of them. They don't do anything, right? The accumulator doesn't do anything. It is a box where the arithmetic logic unit puts the answers to any math, basically. So that's that one. The term clock speed is basically an indication of how many fetch, decode, and execute cycles can be executed per second. Okay, it's measured in hertz, which means per second. You get mega, giga, which mean million or billion, which are the general terms. Now you do get tera, but computers are not doing many terahertz, not unless you've got some sort of supercomputer. So yeah, giga means billion. So 4.2 gigahertz is 4.2 billion FD cycles per second in theory. I'll leave it in theory because you're never sure of what's going on. Right, so why do we load programs into main memory rather than just execute them from the secondary storage? 2 simple answers. The main one is speed. RAM is significantly faster than even a solid state drive. Between 10 and 100 depending on how it's working, and there's lots of different types of speed, like response time, which I won't really get into, and you get something called CL timings and things like that. But basically RAM is significantly faster, and so it's better to have a small loading time while we wait and then execute it from the much faster RAM. Just one thing, a couple of you get confused. RAM is volatile, which means it loses the data if turned off, and your secondary storage isn't. A couple of people got that wrong in the test. So the other reason as well is that CPUs are not designed to directly access the secondary storage. They're designed to access RAM, and so that's where we need to do it because that's the better system. But yes, it's better access, but mostly because RAM is much faster. It might be in the future that we can create RAM that's really fast and really big, because remember, RAM isn't as big as secondary storage. It may be in the future that we don't even have secondary storage, but probably cloud will have overtaken by then anyway, so it won't be such an issue. But yeah, so that's the reason. RAM is just a lot faster than the secondary storage. Yeah, and the last question of the theory section. Yeah, basically an embedded system is just where there's software and hardware together in a usually mechanical system, which basically is a computer designed to do a specialized task such as dishwasher or microwave. The advantages are that they are low power, reliable, cheap to create because they don't need very expensive CPUs to use them because they're normally doing a very specialized task, so you know exactly what you need. And yeah, overall they work more reliably. So now we're going to go into the coding part of it, and we'll look at data types. So a data type basically tells the programming language what does the data mean. Is it a number, letter, string, whatever? This helps the computer to understand what to do when adding. For example, if we add 2 strings together, which is called concatenate, it would put them on the end. So hello Steve would become hello Steve, right? Hello plus Steve would become hello Steve. But numbers would obviously add together. So there are 5 that you need to know in the course. A string is obviously just any collection of symbols or anything you can write on the keyboard in a string, normally done with quotes like this. A char is a single character, anything on the keyboard. There you go, underscores, a version of one. C, a single character. Okay. An integer is just a whole number. A float or a real, they're also called reals. They're also called that in maths as well. Is any decimal place number, a number with a decimal place in it. And then a Boolean is just true or false. Sometimes can represent 1 or 0 as well. They're also useful. But yeah, they're the data types that you need to know. And yeah, that's that one. Right, so this question here, number 2, write a program to allow the user to enter their name. It will then print back hello name. This, so quite simply, let's get out Python. So get them to enter their name, but I'm going to do color. So I want to do the exact answer. Equals input, enter your favorite color. And then I'm going to put print F, because I want to do a formatted string. Your favorite color was, and then in curly braces like this, I put color, like that. The other way to do it, which some of you did in the exam, or some people did, is really, unless you change your mind in between that time, is, and then you do it like this, which it does work, but the problem is, sometimes you can have more and more you've got to write, and it can get annoying. This way is quite a lot easier to do, but I'll just run it. There it is. I don't know. Front, blue, whatever. Your favorite color is blue. So they both work and they both get the marks, and you might think that's easier, but the problem is, what if I then want more words like okay or something? Now I've got to put another comma, then that, and then I might want another variable like hi, and then it can get quite annoying. So I highly recommend you do it this way. But yeah, so that's the answer to that one. Right, this question here, nearly everyone got this question wrong. The only time anyone got it wrong was they incorrectly wrote the printed out of results. Remember, it actually prints either grade A, grade B, or fail. So basically 9, so number equals 9, result equals 9 times 2, so that would be 18. Is 18 bigger than or equal to 50? No. Is it bigger than or equal to 20? No. So that will print fail. The only times that people got that wrong really was they tended to write sort of 18, 50 and 20 in here rather than writing the answers to what will be printed out. But yeah, on to the last one. So this one here, write a program that allows the user to basically enter the length and width and it will print out the area. Now I'm not going to do length and width, I'll do speed over time. So for those that don't notice, speed equals distance over time. Okay, so first of all, I'll get them to enter in the distance. I'm going to call it D, because I can't bother to write it. I'm going to use a float. A lot of people use integer. Remember, it's probably likely that there would be the ability to have decimal numbers. And quite a lot of people forgot this second bracket here. Remember, there's 2 bracket opens, so 2 brackets closed, okay? So that's the distance one. Then I get them to enter the time. And then I work out the speed equals distance divided by time. Now this one here had a specific way it wanted it printed. It wanted it printed like that. So I'm going to do something similar. Print, use a formatted string with a distance of D and notice the curly braces and a time of T. The speed is S. There you go. Notice that I've used the curly braces to print these things out, and I've used F, otherwise I can't do that. I don't know why they don't just make that default now, so it is always a formatted string, but they don't. Everyone says they should online, so maybe they will. I'll run that. Out here, distance is 45, time is 2, and the speed is 22.5, so there you go. That's that. So, yeah, that's the paper. Hope you did well.